Hi all, I'm Pandigital and thanks for joining me. Now if you didn't already know, I'm absolutely crazy about Pandigital numbers. You know, those numbers that contain all the digits 0 to 9. Pandigital numbers exist in all number bases, and that includes the Roman numerals. So let's wind the clock back a few years, take a look. Now, to save some time, I'm going to assume you understand what Roman numerals are. There's only 7 basic numerals, and here they are together with their decimal equivalents. A pan-Roman numeral is simply a numeral that contains just these 7 symbols. It turns out that these 8 are the only pan-Roman numerals there are. Even so, there's still a few interesting things about them. Firstly, if you add up the numerals MDC, etc., you get the numeral MDC LX VI, which of course is just the same numerals in the same order. Quite pretty, but perhaps not too surprising, considering the way Roman numerals work. Secondly, the smallest pan-Roman numeral is a perfect square, the only one out of the 8 in fact. And lastly, these two numerals when taken together contain all 7 symbols, and when converted into decimal, it's obvious they're both perfect squares, which when added together gives 1664, and this, when converted back to Roman numerals, gives you the same answer as if you just joined the original 2 numerals together. It's quite nice, I think, because there isn't a decimal equivalent. Fun fact, by the way, did you know that Julius Caesar was left-handed? Because I didn't. Other than that, I couldn't find anything else particularly remarkable about pan-Roman numerals, so I wondered if I could find anything interesting if I converted the decimal digits into Roman numerals and then joined them together like this. I soon realised that the string of Roman numerals you get can sometimes be interpreted in more than one way. The one I've just shown you can be interpreted in 11 ways, and these 4 can each be interpreted in 42 different ways, which happens to be the most possible. Now, it's not too difficult to work out the decimal equivalents, so I'll leave that to you as an exercise if you want. All in all, there's more than 84,000 distinct Roman numerals, and out of those, there's 14,000 that only have a one-to-one interpretation, and by that I mean there's no ambiguity when you convert from Roman numerals to decimal. And then out of those 14,000, there's only one that is a perfect square, which is this one. Although the Romans were obviously great engineers and builders, they weren't particularly big into mathematics apparently, which is I suppose not surprising considering how baffling it would be if you used the x as a multiplication sign and the strings of Roman numerals I've described in all the calculations. This is the 2 times table written out using this system, which I'm sure you agree is rather confusing. Now, the fact that multiplication is confusing leads to some ideas for nice puzzles. For example, can you solve this product given that both sides of the equation contains the digits 1 to 9? I'll give you the answer to this one just to explain what I mean. As you can see, each side contains the digits 1 to 9. Can you work these ones out then? Again, they contain just the digits 1 to 9, and I'll give the answers next time. It's natural to ask, I guess, if you can do the same thing with all the 10 digits. But here lies a bit of a problem, because there's no Roman numeral for 0. Apparently the Romans used the word nulla to represent nothing, but they didn't have a symbol for 0. There is a way around this, because if you always keep the 1 and the 0 together, you can make 10, and that converts nicely into the Roman numeral x. So the overall result are strings of Roman numerals that look like this. You can do all the things I've spoken about earlier, counting duplicates and multiplication, etc. But the interesting thing is that some conversions lead to what I call imaginary numerals. This square converts to a string of Roman numerals, no problem. Same with this one, and note that the root itself also contains 1 and the 0, 10. But the square root of this one has no conversion because neither of the 2 zeros are associated with a 1. So, although the left-hand side is a perfect square, there's no way to write down the square root. It's almost like the square root is imaginary, just like the square root of -1 is imaginary. And there are a few others, see if you can find them. Last thing I want to show you are these, something that I call augmented Pandigital numbers. They look a bit ugly to me in decimal because the 1 is repeated twice. But in Roman numerals I think they look quite nice because it's, well, like a complete set. Once again, you can do all the things with Roman numerals I've spoken about earlier. Everything that is except multiplication. It doesn't seem possible to me for the product of a set of augmented numerals to equal another augmented numeral. In other words, something like this. As you can see, although the set of factors is augmented, the product is not. The extra one is missing in this case. So I don't think that multiplication is possible. I have a pretty good idea why, but I've struggled to find a proof. So perhaps you can do better, and if you can, then I'd love to know. So multiplication is not possible, but by compensation, augmented numerals can be palindromic, which means some arrangements can be written the same forward as well as backwards. And they can also represent prime numbers, which is just not possible with regular Pandigital numbers because they're all divisible by 9. You can even have augmented numerals that are palindromic and prime. Primes are actually quite interesting. Because a Roman numeral can sometimes be interpreted in different ways, a numeral can sometimes represent both a prime and a composite number at the same time, which is a bit curious. In fact, some numerals can represent more than one prime. This one can be interpreted as 12 different primes. And the only other representing 12 primes is this one, and I'll leave that for you to work out. What are they? Answer next time. And so there you have it. Something different but interesting nonetheless. What I like is there's lots of opportunities for puzzles, and there's quite a lot that I didn't have time for in this video actually. Hope you enjoyed this chapter. I enjoyed putting it together. Please excuse my pidgin Latin though, I don't speak Latin. I use an online translator and I know how reliable they can be. So I'll finish off then with the answer to the Christmas tree puzzle from last chapter. All the best. Cheers.